I'm Sonali Tamhankar. I am a senior clinical data scientist at Fred Hutchinson Cancer Center. Okay, so the thread that ties this conference together is the machine learning and the generative AI piece. All of us come from different industries. So I will begin by telling you a little bit about my corner of the healthcare world. And then I'll present a couple of examples. We will warm up with the regulatory chatbot example, and the majority of our time today will be spent on the sickle cell use case. So Fred Hutchinson Cancer Center in Seattle serves about over 50,000 patients. When I joined this organization over 4 years ago, I joined Seattle Cancer Care Alliance, which is the patient-facing piece of Fred Hutch. At that time, there was a separate Fred Hutchinson Cancer Research Center. So we merged last year to become Fred Hutch Cancer Center. There has always been a close collaboration between the research and the clinical piece. We have a large number of participants in clinical trials. Fred Hutch has over 5,000 employees, including 3 Nobel laureates. In addition to oncology, Fred Hutch also does infectious diseases and benign hematology. So these are non-malignant blood disorders like the sickle cell anemia. So I sit within the enterprise analytics group at Fred Hutch. So on the research side, there are biostatisticians and postdocs who do data science, machine learning kind of work. On the clinical side, we have enterprise analytics group. We work under the quality improvement umbrella. Most of my colleagues are using SQL and Tableau. These are the kind of tools they are using. They are often building KPI dashboards, also clinical outcomes dashboards. That is typically their kind of work. We use Epic for our EHR system. Okay. We have Epic experts who understand the data very well. We also have an educator. So the EHR system, Epic, which is the largest EHR system, they have their built-in tools. So that allows clinicians to get some information about their patient panel. So there is that layer of the EHR tools. Okay, all kinds of things are happening here. Thank you. Perfect. Thank you very much. So we also have an educator who helps clinicians use the built-in Epic EHR tools. Then there is the layer of dashboards that are built by my teammates. I'm the only data scientist on the care delivery side. I'm the only clinical data scientist. So my work is usually more like predictive analytics or use of generative AI. We do have clinical notes in our SQL data mart, so I can do NLP on the clinical notes to extract information that is not available in a discrete format. One constraint in this environment is my business partners are clinicians, so actual providers who are providing care to patients, so their bandwidth tends to be pretty limited. So let's start with the regulatory chatbot use case to warm up. This was one of the first projects that I did in the generative AI space just to learn. So all of us in this room, and also those of you listening online, we are all consumers of healthcare, right? So when we go to the doctor or if we are admitted to a hospital, we want to know that our provider is washing their hands and the hospital is doing everything they can to prevent infection. So healthcare regulations exist for a reason. However, according to an author who has done research in this field, these regulations are neither uniform nor consistent. According to this American Hospital Association website, there are over 600 discrete regulatory requirements, and the organizations spend a lot of money making sure that they comply with these regulations and employ a lot of people. Penalties for non-compliance are usually pretty stiff. So this project was to help our regulatory compliance team by building a semantic search-based tool to look through different regulations. So in this audience, as soon as I say this, I know that a lot of you are thinking retrieval augmented generation, right, RAG. This is what I used to develop this toolkit. So my business partners helped me by finding these documents that they wanted me to look at. And I took these documents, created chunks out of those, stored them in a vector store. I used Fias and LangChain for this project with the lightweight all-mini-LM L6 v2 embedding. When the user query comes in, that is combined with matching splits, and then a prompt is created that goes to the LLM to generate an answer. So the LLM I used for this use case was Llama 2. In fact, keeping with my philosophy of adroit assistance, so right now I feel that with the generative AI use cases, especially in healthcare, it is better to think of them as adroit assistants. I think we would be disappointed if we expect them to be omniscient oracles. So it is, the thought was just to provide the matching excerpts to our regulatory compliance team so that they can take it from there and the final control remains with the humans on the team. The kind of documents that they chose were CMS documents. So this manual is over 500 pages long. RCWs, this is state law, revised code of Washington. And the tool looked something like this. Because this was all in the public domain, I could host it on Hugging Face. So on the left side, I listed all the documents that they picked. There was a place where they could ask the questions, and what it displayed was the matching excerpts. And these links, they would take them to the appropriate pages on the matching. So this project was done a few months ago, and today you can just use OpenAI tools, and you can drag and drop PDF files, and you can have chat against those. There is this step where the domain experts are picking appropriate PDFs. That also adds value. That helps standardize the project. So if you have the whole team, this kind of building a tool like this could still be useful today because that ensures that everybody is looking at the same set of documents. If you have new people joining the team, it helps make sure that they will still be referencing the same documents. So something like this could still be useful today. In any case, it served as a good warm-up case for me. The next use case was the sickle cell use case. So let me start by motivating this. The first time I saw this little illustration, it really made me think. There is the concept of inequality, which we all know, where the opportunities are unequal. Naively, it might seem like once we have equal tools, we are done, right? However, in real world, opportunities can still remain unequal. So the concept of equity is where you provide appropriate tools to ensure that everyone has access to equal opportunities. And then there is the concept of justice, which goes one step further, where you kind of fix the root causes, right? So where you make sure that the environment itself becomes more equal. So I was listening to the previous speakers and talking to a lot of you today. I feel that people in this room, all of us working in the field of generative AI, sorry, better? Is this better? Okay, sorry. I hear differently, so I don't know what you are hearing. Apologies for any problems. Okay, thank you. Yeah, so people in this, I was just giving you a compliment and they interrupted me. So people in this room have such power, right? So all of us have the power to make a difference through the choices that we make, the choice of problems that we choose to work on, the data we choose to train on, the models, and the tools that we use. So it was my privilege to work on this problem of sickle cell anemia. Majority of people who have sickle cell anemia are people of color. According to some estimates, it is 86% of people. And people with sickle cell disease, they have painful episodes called crisis. These can last from hours to days. And some people have it every few years. Some people have many episodes a year. So they are often seen in emergency rooms. Patients with sickle cell crisis, pain crisis, are often seen in emergency rooms for vaso-occlusive crisis. So what happens is they have these HbS, hemoglobin S, and when those cells are deoxygenated, they form the characteristic sickle cell, and they become sticky, which is what causes this occlusion in the blood vessels. There are drugs that help with this kind of a disease. A number of these visits can be preventable. Up to a third of these visits, according to some estimates, are potentially preventable. So the project that we did was to try to find the patients who are at highest risk and then try to find out what are the drivers and what kind of tools we can design to intervene. So I took this as a twofold project to create a sickle cell ED visits tool, combining the piece with traditional machine learning and the generative AI piece. So let me tell you a little bit about this tool. The data came from our EPIC EHR, so this is actual patient data. The EPIC has this chronicles piece, which is the live piece, and then on the back end, it has SQL data mart clarity. This is where I pulled my data from. So I picked a cutoff date, and all of my features came from a year prior. My population was defined as patients who have sickle cell anemia. So patients with sickle cell trait have only one copy of the defective gene, and typically they don't show symptoms. So we excluded patients with just sickle cell trait, and patients had to have at least 2 visits to name them as our patients. I pulled a whole bunch of features, including demographic features, clinical features, operational features, like past emergency room visits, and so on. And my target variable was emergency room visit in 1 month after the cutoff date. So this was just exploratory analysis, just looking at the data. This is, each bar here represents a patient. So you can try to imagine the quality of life for somebody who is being seen in emergency room 41 times in a year. We had 136 patients in the denominator. And in our data, again, we saw that most of these were patients of color. These are all very young people. Continuing with the exploratory analysis, these are some of the reasons for visit. So they are being seen in the emergency room or even outside of emergency room, primarily for pain management. There are the sickle cell pain crisis. There is also the care navigation and so on. These were some of the labs. So the outside teal color are the low lab values. So these patients will often have low hemoglobin because the defective cells, they are shorter lived. They live for like only 20 days as opposed to the normal red blood cells, which live for 120 days. So they will often have low hemoglobin. These ones are higher values and these ones are abnormal values. So after just looking at some of this data, I built a model for to classify highest risk patients. So all of these features, right? So we had all these different medications, different reason visit names. So all of these became features. I removed the infrequent values and then created features like this. So reason visit name for pain management, how many visits a patient had for pain management, and so on. So all of these became features. I started with some 372 columns and then just looked at the correlation with the target variable to keep the top 50 columns, did a train test split with about 200 estimators or so on. I did not really play a whole lot with these pieces because the area under the curve was reasonably acceptable right here. So I can definitely do a lot more here too. But the question I wanted to also ask was, building the model is one piece, but we are not done, right? I mean, all that once I have a model, it's just something on the computer. How does that help the patient? So what do we do next? Okay. While this is happening, I want to maybe take questions. Are there any questions so far? Okay. Yeah, we can move on. Okay. So yeah. So once we have the model, there is still more to be done because we want to help providers to give them some understanding as to why certain patients are at highest risk. Just giving them a list of patients may not be quite as helpful because providers are often overwhelmed by the amount of information that comes their way. So I use Shapley values for this. A lot of you may have heard of this concept. So this is an explainable AI method. So the idea is that the cohort risk for the average patient is here, a particular risk patient is over here. So what explains this difference, right? So out of all the features I have, which are the features that are causing this particular patient to have their risk to be here when the cohort risk is here? So the Shapley values can explain some of that, and that makes this more actionable for the providers to design interventions. The other piece I wanted to include is the new tool we have, the Generative AI tool, which allows us to converse with clinical notes. So again, we want to make sure to stay as close to the source as possible. We don't want creativity here. The mock-up for my tool. So on the opening screen, I listed the highest risk patients, their MRNs, and then there is a place for the provider to enter a specific MRN. Once they do that, then more information pulls up. So I can show dates for emergency room visits or pain score or something like that. This is where I show Shapley value plot. And then I have a tab where the provider can chat against patient notes. And then again, staying close to the source, I can also display the exact notes. This is the actual tool. Of course, this is all PHI, right? Like I'm sure, so this is a clinical intervention tool. So it has to live within our firewall. And the first thing I have to do is to ensure provider credentials. Once they enter their credentials, then on the sidebar, the list of highest risk patients shows up. Of course, what I'm showing you here is not PHI. This is all made up data. Once they see this list, then they can enter a specific MRN, and then more information about that patient shows up. So their emergency room visits and their pain scores. Pain score is an interesting concept. So it is subjective. So my pain, so that's just the answer to the question on a level of 1 to 10, what is your pain level? So my 5, maybe your 7 or your 9, vice versa, right? So it's subjective, but it still has some information, as in my 5 today and my 7 today might be comparable, or just how many times the question is being asked, or if the patient is repeatedly reporting high pain, then maybe there is a way to intervene before they actually end up in emergency room. So some information like that could be useful. And this is the Shapley value plot. So what I'm showing here is the feature, so reason, visit, name, no-show, and then I'm showing the patient value. So this particular patient had 6 visits that were no-show in the past year, whereas the cohort average is 0.82. So no-show is where a patient hasn't canceled, they just didn't show up for the visit. So then there is a place to enter questions. And the provider can ask, why did this patient miss appointments and how many appointments they missed? And now, like our warm-up case, right? So this is on the back end, the same thing is happening, except instead of the documents, I'm now chatting against patient notes. And my metadata here is the patient MRN and the visit date. So when the provider asks a question like this, matching excerpts are again pulled up with the date is displayed. Right now I'm also showing the answer because the provider that I'm working with, he is really savvy, he understands the limitations of LLM. So we are kind of exploring how useful is this. So I have 2 tabs here. I have the relevant note excerpts, which is this tab, and then I have the full text tab. So once they have this note, this date here, and again, this is all made up data. There is no, perfect. There is no Dr. White code. This is all made up data again. So once they have the date here, they can go to this other tab and then find the full text. So they can go to this tab, they can have the encounter date, and then they can investigate further. So the idea is to kind of bring all of this together, have the piece, the traditional machine learning piece, where we have the typical risk models and so on, and then to combine it with these new tools that we have now, where we give the provider the power to investigate further, dig deeper, so that they can design interventions for specific patients. So all of this is work in progress. It's been fun to play with all of these tools. And again, being the only data scientist, there's only so fast I can go. So I want to validate, refine, work with our providers. The model itself can be improved, the interface can be improved. A few months ago, I did not know Streamlit, so again, experimenting with things. I want to widen the scope to ED visits for all patients. So this one was ED visits for sickle cell patients. All patients will be It will be a bigger population and it will be more diverse because then patients are coming in, the emergency room visits can be happening for multiple different reasons. In fact, I'm spending half of my time at Fred Hutch today and the other half with, so NIH has this Aim Ahead consortium, which sits at the intersection of artificial intelligence and health equity, which is perfect place where I want to be. So I'm doing a leadership fellowship with them. So that is going to be my project for that, for Aim Ahead. There are technical pieces, there are infrastructure considerations. To scale up, I might need to change the infrastructure I'm using, use different vector bases and so on. Also, potentially I could use agents. So depending on the questions that are being asked and depending on what the Shapley values show for a particular patient, I can show different kinds of data to the provider. So that is another piece that I can play with. So we are on my last slide. So I hope you got some glimpse into the healthcare ecosystem, at least my corner of it. Partnering with domain experts has been crucial, and there are enormous opportunities to build tools that combine traditional machine learning with generative AI. If there is one thing that I want to take you from this talk today, it is this, that each of us has the power to make a difference through our choices in our daily work, especially working in the field of machine learning and generative AI. And I do really request all of you to continue using it to create the world we want to live in. Thank you.